Okay, so in the last video we were talking about the audible range. So for humans, the stereotypical normal human, the audible range is between 20 hertz and 20,000 hertz. At this point in your life, you can probably hear up to maybe 24,000 for some of you, but not all of you. And as low as 20,000. Below 20,000, we just feel the vibrations, but we can't hear it. Our ear do not detect those vibrations, our eardrum, as being together. They're too spaced apart in time that they feel them as separate vibrations. Whereas 20,000 and above, it's like 20,000 times a second. Our ear can't handle that many vibrations. It can't interpret it. There are other animals that can. Dogs can hear up to 50,000 hertz. Bats use ultrasounds to navigate. They can hear up to, we think, 100,000 hertz. Dolphins as well are ultrasonic. Okay? I was about to, as the video ended, tell you about a mosquito ringtone. Back probably in the late 90s, early 2000s, after cell phones came out, but when people still used to actually call each other on them as opposed to just text, students would get in all kinds of trouble because their phone would ring at the supper table, in the classroom, at church, after they were supposed to have it turned off and be in bed. And so there was a marketing scheme that began with something that was called the Mosquito Ringtone. Now, it really came about from a shop owner in, I forget now if it was London or Dublin. He had this cool little shop of trinkets right on the corner, I think it was London, right on the corner in the city. But teenagers used to hang out in there because it was a convenient location. They never really bought anything because they didn't have money to buy anything. But they scared away the paying customers because the paying customers would come along and see a bunch of these hooligan teenagers. You know I'm joking when I say hooligan, but people who don't know you might think it. And they wouldn't come into the shop. But the teenagers weren't doing anything wrong, so he couldn't call the police to come and get them because they were just hanging out. So clearly he was a physicist. He came up with an ingenious solution. He began to play a high-pitch hum, a high-frequency sound that the teenagers could hear, but the paying customers couldn't. It didn't take very long before the teenagers stopped hanging out there because the high-pitched hum is painful to the ears. Not long after that, cell phone companies realized they could market that same hum as a ringtone that teenagers could then download and play. And people wouldn't hear it. They could use it as their ringtone and people wouldn't know that they were being called in class or in church or late at night. So it's called the Mosquito Ringtone because it's a high-pitch, rather annoying hum, just like a mosquito. And so I'm putting the link right after this video. I will put the link to that to a page that will show you a little blurb about the ringtone. It says teachers and parents can't hear it. But then I want you to scroll down a little bit. I don't actually want you to download it, but scroll down a little bit underneath the big green start button, and it lists frequencies, and there's a little play button that you can play to see if you can hear it. And those frequencies start at 8,000 hertz and go all the way up to 22,000. So try it and see when you drop out. I can hear up to 20. I can't hear 21 and 22. It says that only 18 years old and younger should be able to hear that, and that's probably why. I drop out after 24, so I'm a little bit older than 24, so I guess that's why. All right, the last little note on frequency here is that every vibrating object produces a sound. But whether or not we hear it depends on if the vibration is in the audible range. Okay, so every vibrating object here produces a sound. We might just not be able to hear it. If we go back to music, since we started frequency with music, there are a whole bunch of different classes of musical instruments. For example, the drum, the loudspeaker, the cymbal, these are in your notes, by the way. And the vocal cords, what's vibrating in those instruments? the instrument itself, right? The bass of the drum, the cymbal, the vocal cord, they're doing the vibration, producing the sound themselves. The next class includes the trumpet, the trombone, and the tuba. I believe those are called brass. And what's vibrating there are the person's lips. The third class are the reed instruments, the clarinet, the saxophone, the oboe. And what's vibrating there is the reed, the thin strip of wood that goes through the instrument. The next class, flutes, recorders, organ pipes, whistles, they're the wind instruments, and it's the air in the column that's vibrating in that one. And the final class are the stringed instruments, and lo and behold, surprise, surprise, it's the strings that vibrate there. All right, our next topic is something called the Doppler Effect. And it comes into play, you would have noticed it in your light, if you were ever standing outside when an ambulance, a fire truck, or a police car comes up the street with lights and sirens. Well, who cares about the lights, but sirens on. Okay? If you've ever noticed that, and if you haven't, I want you to this summer, when you hear them approach, the frequency of the sound that you hear will appear to be different than the frequency as they go away from you. And that is because of what is known as the Doppler effect. So if this is my source and it's stationary, then as it sends out sound waves, they're all going to be equally spaced apart, or at least as equally as my artistic ability will allow it. So it doesn't matter if I'm standing on this side or on this side. The frequency of the sound that I hear is exactly the frequency that the source is emitting. But now, imagine that the source is moving. So here's my source. So it has sent out a sound wave initially, and really, right, the first one it sends out will be the biggest because it will have traveled. And now it moves. So I'm going to have my source move this way. So now its center is over here. So now its sound wave is closer to the previous one on one side and further from it on the other. It continues to move. Oops, that shouldn't really be touching. Sorry, a little bit too close. It continues to move. And as it does this, what's going to happen is if you're standing on this side, you're going to hear a frequency that's higher than if you're standing on the side that it's going away from, right? This person will hear a higher frequency, and this person a lower. Not because the ambulance or the police car or the fire truck has changed its frequency, but it's because the observer and the source are getting closer together. And as the source moves towards the observer, or the observer towards the source, it could be as well, the sound waves that are being emitted are beginning to stack up. Whereas when it's moving away from the observer, now not only, like, it's not the regular space, but now the source is further away when it emits the next sound, the next wave front. And so over here, it appears that the frequency is lower. Now, if the source could actually move at the speed of sound, what you would end up getting is that all the wave fronts on one side would end up piling up on top of each other. And so and what forms here is known as a sound barrier. So this is when the source is traveling at the speed of sound. So the source will be equal to the speed of sound. And then if the source speeds up and goes through this, they'll be breaking what's known as the sound barrier. Whoops, I already wrote that down. And breaking the sound barrier happens when the source's speed is greater than the speed of sound, and that's when you hear a sonic boom. Okay? So I'm going to have to come back because we're almost out of time on this one for just a couple of minutes to make sure you got the Doppler effect. But really, it's the apparent change in frequency as the source and the observer are moving relative to each other. So one is approaching the other or one is receiving.